So this is our Target 500. The first thing I'm going to do is check my comms. And right now I'm interfacing with the PLC through my Ethernet IP. So we'll see if it's there. So it's not there so here's Ethernet IP, there's my PLC. So now I'm ready to program, right? So I'm going to come up here, I'm going to select a new program. I'm going to go down here and select the MicroLogic 1100. Series B. Okay. And then I'm going to come up here and I'm going to insert a few links. We'll come up here and put this guy, this guy, this guy. And over here, generate output. Down here, what I'm going to do is I'm going to take these contacts and I'm going to put them in series. Then I'm going to put an output. I'll do addressing here in a minute, guys. And then I'm going to come over here and I'm going to come over here and do this. So you usually have to do that. Now to drag it, what you do, don't try to drag on the address bar. Come down here on the bottom, and then just click it, and then you can drag it. So I'm going to bring that inside, and I'm going to bring this like this. So here I have 3 devices. I'm going to come up here, we'll call this input 1. We use input 0/0. I'll hit enter, and we'll call this input 1. I'll input 0. Okay so far. And then over here, I'm going to call this, I'm going to address it output : 0/0, hit enter, and I'm just going to call this A. And down here, I'm going to come over here, and I'm going to call this input 0/1. And somebody here is going to make that mistake, because the 0 and the 0 and the O key is right there together. I'm going to hit enter. We'll call this input 1. Then I'll come over here. I'm gonna come over here and delete these. What I just did, I'll show y'all later on. So what I'm going to do is, let me select the row here. I'm going to come over here, and I'm going to call it B3, : 0/0. I'm going to call it A. And this is input 1. Call this B3, : 0/0/1. I'm going to call this B. Down here, this is going to be input : 0/2. Call this input 2. And we'll call it B3, : 0/2. Now the problem is, how many output ports do I have on this PLC? 6. Okay. So I'm going to run out of those real fast. So one of the major advantages of a PLC is if we've got relays that don't have to control an output, then we can use what we call an internal port. This is in memory. So this is not going to generate, this B3 is not going to generate an output, but I can use it in decision making. And we'll call this, so these are called internal ports. I'm going to call this C. So now I got names. So what can I do here? I can come up here, I can call this A, I can call it B, I can call it C, and it automatically, it automatically filled in the information for me, right? Now here I'm going to call this output colon 0/0, and we'll call this guy here A and B. And now I'll call here, I'm going to call this A, call this B, call this C, and then over here I'm going to put an output colon 0/1, and I'm going to call this 4. Right, what I'll do right now is I'm going to eliminate this wrong right here, and we'll add some more later on. I'm going to check for errors. Looks like we got no errors. So I'm going to come up here, and I'm going to come up here, and I'm going to download this to my PLC. I'm going to download. This is where we give it a name, so I'll call it logic. Then I'm going to say, okay. Downloading program. Do we want to download it? Are you sure? Do you want me to switch it from the run mode to the program mode? So how many modes do we have for our PLC? That's a really good question. How many modes, as far as communication, how many modes can we put our PLC in? So we put it in 3. What is the 3? Huh? No, offline is the application. PLC has 3. You can see 2 of them right here. Run mode, program mode. So if I'm going to download a program into the PLC, it's got to be in the program mode. That way it's not trying to run something while I'm putting new stuff in. And then we have the remote. So when we have it on the remote mode, my application can switch it between run and program. If I don't have it on remote, then I have to switch it between run and program. Y'all understand that? So if I didn't have mine on remote, so sometimes this is actually a switch on your PLC. This one, let me bring my camera back up. It won't let me do it while I'm doing it. So I'm going to come up here. Let's go ahead and download it. Then it says it's going to do back, what's it going to do for me? It's going to switch it back into the what? The run mode. Do I want to go online? What's online? This is not the PLC. This is the application. I'm putting the application back online. So right now we can have our application in 2. We can have it what? Offline. What can we do offline? We can modify a program, or we can do what? We can create a program. Online is when we're actually monitoring what the program is doing. Okay. So I'm online. So let's see if I can break up my camera now. It still won't let me break up my camera. So I'll just have to show you. Yeah, so my camera. Oh, dang it. So we go to mode selection. It's in our menu, guys. I'd have to show you that. My camera disappeared. Okay. So right now we're in monitor mode. I'm going to come up here and reduce this so we can see our whole program. So this is called an internal coil. What is that? That's a coil that does not generate an output, because we've only got 6. So if I come over here and use one of my outputs and I don't hook anything up to it, then we've wasted an output. We've only got, 6. So PLCs have used what we call internal coils for years. Now I'm going to come over here and I'm going to close this switch right here. So that's A. Well, what do we know about this AND output? What do we notice about the AND output? So to make this output go true, I've got to have A and B and C. Or all of them has to be true. Now look at this one right here. So on this one, output 1 is true. It's a what? It's an OR. So A or B or C has to be true to cause this to happen, right? Does that make sense? So I can turn off A. I can bring in B. This is still false, but this is true. I can turn off B and turn on C. This is still false. This is true. I can do A, B, and C, and now that guy right there goes true. So this is AND logic. How many of these contacts can I put in series like that? I've got 3. How many do you think we can do? On our PLC, I could do 10. Because why? That's how many inputs we have. But literally, we could use all 10 of them in our logic, right? Or I could have, so we could use all 10. So, but if I hooked them if I hooked normally open in series like this, or examine it closed, in series, that would be an AND. So right now, got to have at least how many to get an AND? Got to have at least 2. 2 or more. 2 or more. And it all depends on how many, in this case, it depends on how many inputs you got. So the maximum number of inputs I got is 9 or 10, right? 0 to 9. Everybody okay? Okay. So let's say I come up here, I'm going to take this, so I need to do my program. I'm going to take it offline. I'm going to come down here and I'm going to add another room. Here I'm going to put an examine if open. And I'm going to assign this to A. And then I'm going to put this guy right here. And I'm going to assign it to output : 0/2. Okay, and I'm going to call this a NOT. Check it for errors. It says it's okay. And we'll go ahead and download it. But yes, we'll save it. Revision. So I could put a revision number so I know now I'm going to have an A out there. I know this is my second revision of this. Oh my goodness, what did I do? Yes. It wants me to start a new program. Do y'all see what I did wrong? Well, guys, no, there it is. Now, when I uploaded, what did I lose? I lost my symbols, right? So that's one thing that RSLogic 500 does. It does not put the symbols in the PLC. So when they recompile it back into a high-level language program, we lose our symbols. Most of your new applications, they do that. They save the symbols inside the... But if I need to do a symbol, I can right-click, choose Edit Symbol, and then I'll call this input 0. And I'll call this input 1. And I'll call this input 2. So how am I doing this? I'm right clicking on it and choosing edit. And over here I call this what? Call this A. Call this B. Call this C. Y'all understand internal coil? What's an internal coil? What's an internal coil, Chris? Jacob, what's an internal? Corey, what's an internal? It's a coil. It's a coil that doesn't need an output. All these contacts are in my program. It don't need an output. It don't turn on the light. It don't energize a solenoid. It don't run a motor. So we have the ability to do what we call internal coils. These are coils that are strictly, the contacts are in the program. They don't need to turn a light bulb on. They don't need to turn on a motor. Right? You understand? Because if I assigned that to an output, I would run out of outputs trying to do this program. Because I've only got how many? I've only got 6. So I'm using outputs for things that don't need to turn on anything. Right? You understand? Y'all understand that? So an internal coil, these are coils that don't need to do what? They don't need to generate an output. And it picked up my symbols as soon as I signed those. So I don't know what happened, guys. So I'm going to go offline. Offline. Okay. I'm going to save this guy. Because my data table was changed. Okay. I'm going to add a rung. I'm going to add a examine if open. I'm going to assign it to A. And then I'm going to use another output, which I have now. I'm going to assign this to an output so we can see a light turn on. 0/2. And then I'm going to call this a knot. Okay. So check it for errors. Okay. Download. Oops, something. Download. Okay, I want to give it a revision number. I'm going to say okay. I'm going to switch it what? We're going to download it to the PLC. Now it's giving me a warning because what's going to happen to the program that's in there? It's going to be overwritten, right? Do I want to switch it to the program mode? Yes. Do I want to switch it to the run mode? Yes. Do I want to go to long run on? Now this is the only thing we're using here is A. So notice so when A is true, this is false. When A is false, this is true. So this is what we call a NOT. So NOTs, NORs, and NANDs are what's required to turn it off. ANDs and ORs are what's required to turn it on. Does that make sense? So let's go back. I don't know what I did while ago. Let's go back offline. And then I'm going to come up here and add another rung. Let's add 2 rungs. Okay, I'm gonna grab these. Put 3 of them in series. This is gonna be A. This is gonna be D. This is gonna be C. Then I'm gonna add an output so we can see the light turn on. Output colon 0/3, and we'll call this a. Then over here, I'm gonna put a 1. I'm gonna put a down drop. I'll come up and put another down drop. I'm gonna slide this guy into here. I'm gonna put another examine it open. Examine it open. And I'm gonna call this A. Call this B. Call this C. Those are being controlled by our internal pulls. Then I'm gonna add another output. And call this output colon 0/4. And we'll call this check for errors. Looks like I don't have any errors. I'm gonna come up here. I'm gonna do what? Download it. This is our second revision. Tells me, okay, you're gonna wipe out your program. Do you want to proceed? Sure. Switch it from the run mode to the program mode automatically because I got it set up for mode. Switch back to the run mode and then go online. So right now I don't have any of these inputs true. So notice, none of these are true, so your ands and your ors are false. But when I get down here to this guy, it's true. This guy's true, and this guy's true, even though my 3 inputs are false. So nots, nands, and nors, our inputs are going to make the run go false. Ands and ors, our inputs are going to make the run go true, right? Does that make sense? So notice these right here, the rung starts, if none of my inputs are active, these 2 rungs are false. But these guys, my not, my nor, and my nan, these inputs are what? Oh, it didn't pick up my label then. Now the problem we have is people see this and they learn this as an and. But we got 2 terms that we're going to use. We're going to use any and all. If I say all, it's either an and or a nan. If I say any, it's either a nan or a not. a nan or a no. So what do I say right here? Well, I say all these inputs have to be true before the output goes true. That's an and. Over here, I would say if any input is true, the output would be true. That's an or. Down here, this is a not. You just have to know that. That's not fair. Down here, if any input goes false, if any input goes false, the output goes false, right? You understand that? Or, I'm sorry, if any input goes true, the output goes true. Because true is this up here.
Could you typically use program it so that the emergency stops on the machine?
Oh yeah, emergency stop is nothing but an and. If you either got one button or you got a bunch of them in series, right? It's not a nan, it's a nor. If anybody hits an emergency stop, so y'all see, I can come back here and do what? Another thing. I'll come anywhere you're on this line and do what? That's gotta be what? It's gotta be E. E good first, gotta be. So right here, any one of these So people though, what we happen is people will see this and they learn this as an and then they see this, they want to call this a NAND because the contacts are in series. But what we're looking for is any, right? So if any of these inputs, so these are my control, if these go true, then the output's going to go false. So we can't look at these. We have to figure out what's controlling those, right? You understand? So if any of these inputs go true, the output goes false. So if I say any, it's going to be a NOR because, and if I say false, it's going to be what? It's going to be a NOR. So ORs and ANDs are what's required to make the output go true. NANDs and NORs are what's required to cause the output to go false. And also the NOT. But the NOT you can't use any or ORs. So a lot of people will see this and they want to call it a NOT, but it's not because I have more than one. So a NOT will only have how many contacts? One contact. If you see more than one contact, then it's not a NOT unless it's the only one in the circle. So that's our 5 basic logic gates, guys. So we have 5 basic logic gates, and believe it or not, all digital logic. So if you get into if you take digital and you'll get into comparators, you get into adders, you get into subtractors, all digital logic is made by these 5 basic logic functions. ANDs, ORs, NANDs, NOTs, and NORs. Now, let's take this offline again. And let's put another rung in here. Let's put a that guy, and we'll just control it with A. And I'm not going to sacrifice one of my outputs, so I'll use an internal core. B3, and I don't know where I'm at, I think 4. Colon, 0. By B3 files, we got 256 of these. Our inputs, we've only got 10, right? B3, you got 256 in there. Actually more than that, 256 words. I'm going to check it. What logic does that guy do? If the input is true, the output is true. If the input is false, the output is false. So that guy doesn't do any logic. So one normally open contact by itself does not do any logic because it doesn't change anything, right? So if I close switch A, the output goes true. If I open switch A, the output goes false. So in digital we call these buffers. So buffers don't do any logic. They're either in there for isolation or they're in there to increase what we call fan out. But an internal coil, what's an internal coil? It's a coil that does not generate or does not use one of your precious outputs. So it's in there strictly for logic. It's in there, all its contacts are going to be inside your control. It's going to be inside your control code. And every PLC I've ever used has those things. Because you're only going to have a limited number of inputs on your PLC. But how many B3 files can I have? I can have, until I run out of memory, B3s I could have 256 words. And words are 16 bits. So I could have a lot of B3 files. So that'd be 256 words, right, times 16. So that's how many B3 files of coils I could have. How many inputs can I have? Well, I can only have, 10. How many outputs on this PLC? I can only have 6. The B3s, basically, and I can add more B3 files. So if I need more B3 files, I can come up here, need more B files. I can come up here when I'm offline. I can actually do that online. I can add a new binary file, file 9, instead of B3. I could call this, or name it. I'm not going to call it B3. I call it B10. I could say OK. And now I got a whole new set of B files, right? As long as I've got memory. So that's the power. So in PLCs, if the coil does not generate an output, if it don't need to turn on a light, if it don't need to energize a solenoid, if it don't need to turn on a motor, if it don't need to bring in a relay, then we'll use what? We'll use an internal coil. if it's got to turn on a light, or it's got to turn on a motor, or if it's got to turn on anything outside of the PLC, we'll have to use one of our outputs. So every PLC I've ever programmed has what we have the ability to use what? Internal core. So remember that. So I've heard people do that. They'll sign outputs and they say, well, I don't know who to go with. But the problem is they're doing an output that don't require what? They're doing an output that you're using one of your output ports that's physical. You only have so many outputs available. So we use B3. We use the B3 file for several different things. But look, these are physical. So I can't add, the only way I can add more outputs and the only way I can add more inputs is to add modules. So that's why we don't have to specify the file number for inputs and outputs, because they're physical, right? They can't move. But how many B3s can I have? So right now I got a B3 and I got a B10. So I can come up here instead of using B3 right there, it's offline. No, it is offline. Now I can come up here and assign this to B10 colon 0/0. No problem at all, right? So it worked fine. I come over, check it, it's fine. So how many B3 data files, how many binary data files can you have? So I just made this guy right here. This one came by default. B3 came by default. I just created B10, right? And how many can I create? Well, I can create as many until I do what? Until I run out of memory in my PLC. So all these down here, we can create multiple of these. So more status files, if I need more status files, if I need more binary files, timers, counters, control files, data files, integer files, F8 or floating point files, I can create these. These, we don't have to specify the file number because these are fixed. We can't add more than that, right? Does that make sense? So I can't make another B3 because why? Because you've already got one. But I can make a B11, and we can take these all the way up to 255, by the way. And that's the maximum they let you go. So I could have a lot of B3s, I could have a lot of timers, but it eats up a lot of memory. So that's logic, guys, and that's what the book talks about. So it talks about logic. And what it does, it comes up and gives you the symbols. Let's see if it does. Faults, highs, lows. Truth table. This is where we come in and set up what state the input causes the output. So right here we see what we have two indicators that cause the output. We're not going to deal with Boolean algebra. What Boolean algebra is, by the way, we don't have squares or anything like that. So this represents OR. This represents, that's a low active input. But what we could do, anybody have algebra? What's one of the main things you learn in algebra? Equation reduction, right? So you have a big old equation and you learn how to combine things and add things and cause the equation to get smaller. We have the same thing in Boolean algebra, but we use letters to represent inputs. And then what we can do is if I can reduce this equation, then I'm literally reducing circuits. So that's the big thing in Boolean algebra. It's an equation that represents a circuit, and if it reduces, you'll actually do what? So I was out when I worked at U.S. Steel, they bought a new electroscale on we call it the line scale. It was an electronic scale. And they didn't buy when they bought the scale, they didn't buy an auto zero. And so we like these big scales to have auto zeros because trucks are constantly dropping stuff. So what happens is over time, the scale would actually be weighing 1,000 pounds, and when the truck wasn't on there, it's just junk that was dropped on the big scale, right? So big scales like that, we like to auto zero it. So what we do is we come up, there's a zero on the button, but a truck driver's not going to get out of their truck, go up on the scale, and auto scale it before they drive up on the scale. So I was tasked with designing a circuit that would do an auto zero. So I don't forgot, so like every minute, if there wasn't motion on the scale, so it had a motion sensor. So if a truck started onto the scale, you don't want to auto zero when the truck something's going on the scale. And then I looked at all the outputs to see if it had any weight on there. So I came up with this big old complex circuit, and I took it into my boss, Grady Vines, and he said, Rich, let's see if we can set up an equation for this circuit. And he set up the Boolean equation for that circuit, and he reduced that down, guys. It was unbelievable. To probably one or two integrated circuits. And we put it on there, and if they still got that electric scale out there, it's probably still running my auto zero circuit. But that's the power of Boolean algebra. So we're not teaching that, and the book gets into that a lot. But we're not going to teach that because we're not designing. We're taking circuits that are given. But yeah, if you can do this in digital, if you can set up an equation for a circuit, all you do is so you put a bar on it, put that little dash on it. Normally we put a bar above it, but that little dash means it's got to be off. So if we get this digit right here, so A has to be off, B has to be off, C has to be on, so we put that in our equation. Not A, not B. Or, so you can see we got another one. Another one that gets one. It's going to be not A, B. Not A, that's a little half point, B, C. Then we have A, B, not C. So that would be A, B, not C. A, B, now we have an equation for the circle. And this is next. I can see it's going to reduce already. How do I know it's going to reduce? So I've got a C right here, I've got a C right there, I've got a C right there. I've got an A, so I've got like terms. I can see like terms in there. I know that circuit's going to do what? It's going to reduce. And if I know how to do Boolean algebra, so that's the actual circuit. This is the reduction. So this is me reducing. So rearrange them. Knock down the C, knock the C. So this is what it comes up to. A, B, not A or C. So this is the original circuit. And this is what it turned out to be. So that's the original circuit on the way the person thought this thing was supposed to work. And this is what it came out to be. So that's what we're saying. If you've got an idea in your mind and you can set it up as an equation and you can reduce it, then you can save a lot of programs. So we need to look at symbols. This is in that test. By the way, one of the methods that we program a PLC uses ands, ors, not. They don't use these symbols. These are ANSI symbols. Anybody know what ANSI stands for? It's an acronym. Have y'all heard that before? It stands for the American National Standards Institute. So you can guess other countries over a while, you know. So we set up ANSI. It set up a bunch of standards which are still in play today. But this is American standard. What we've done is there's an international standard put out by the International Electrotechnical Commission, IEC, and they've changed the symbols a little bit. And we can program one of the programming languages we have available, not on this PLC, is using these IEC symbols to represent the devices that we can actually write a PLC program. But in this class, the book teaches these the ANSI symbols. So this right here, this is a symbol for an AND. We got at least 2 inputs, but we could have more. So this is a symbol for what? An AND. This is a symbol for an OR. At least 2 inputs. We could have more. This is a symbol of a NOT. Some people call it an inverter, by the way, but in logic, it does what we call NOT logic. So this is saying if the input is true, the output's false, right? This is a symbol for a NAND. And then this right here is a symbol for a NOR. And that's your 5 basic logic. So your NANDs and NORs says this says if all these inputs are true, the output goes false, right? Understand? This says if any input goes true, the output goes false. This says if all these inputs are true, the output is true. This says if any input is true, the output is true. So that the circle out there means it goes false, right? If it don't, it means it goes true. That makes sense? And if you learn these, you just have to adopt symbols. So for AND gate on IEC, it's a rectangle like this. We bring in our inputs, and then they put the AND symbol in there. And that's the only difference. So if you understand this, then it would be real easy for you to adopt that over. I'll try to do it. We can't do RS Logic. The only programming language that RS Logic 500 supports is Latin. The Studio 5000 supports ladder. It supports function block programming. It supports function diagram programming and structured text. So what it does, it gives a route for people. So originally PLCs were for electricians. They understood the ladder logic. So they understood the ladder logic. That's the way we want to program, right? It would be real easy for them to adopt that. But now we have people coming up through computer science. So we want to give them a method of programming, right? On the languages that they understand, like Pascal and C++ and those high-level scripted programming languages. So we have one of those. We have people that come up through electronics, and they know ANDs, ORs, NANDs, NOTs, NORs. They know shift registers and all that kind of stuff. So we'd like it to be able for them to do what? Program that without learning ladder. So now most of your PLCs have multiple languages that's available to you. But all of them still support one. I wish I could find one. We had a little GE Series 1 that programmed in Boolean. You'd say start rung, and then you'd say this, and with that. So you would actually have to enter it like that. You didn't have any symbols at all. So NOT, everybody okay? This is the truth table. So A is the input, output. If the input is false, the output is true. If the input is true, the output is false. This is an AND. So this says, notice all they're doing is counting. So A and B, 0, 1, 2, 3. So notice all inputs have to be true before the output goes true. Are we okay? Now this is a NOR. If any input is true, the output is true. I don't like this because it's not really like that way. This is a NAND. So NANDs, NORs, ANDs, and ORs have to have at least 2 inputs. Most people only draw 2. Because the more inputs you have, the bigger the truth table is going to be. So we can have up a 7430. It's an 8-input NAND gate. So it means that sucker would have 256 entries in a truth table. So we don't deal with truth tables very often, because if I learn a NAND gate says all highs to get a low, then I don't need a truth table. Right? Does that make sense? So truth tables are nice. They prove that you know the way it occupies. But once you get past 4 inputs, which gives you 16 combinations in your truth table, once you get past that, then truth tables become very cumbersome, right? There's a method of reducing called Karnoff maps. Nancy loves them. Karnoff maps, though, works good up to 4 inputs, but if you get that fifth one, the tables get so big it makes it real hard to work with. Try to figure them out. So this Indian off, we had a guy, he graduated, I can't remember where he graduated from. Since I'm an Auburn fan, I'll say Alabama. And we had a bunch of digital friends. This guy actually had a strong table above the plate. So he didn't learn keys and all. He learned this table. So instead of saying all highs get a high, he had to go to the table for an end table before he played. So now y'all know I'm an Auburn fan. Plus my dad was an Auburn. And I went to Auburn, by the way. I didn't graduate, but I went. So this is the north. Key high is low. So it's the north and out. It makes what? 2. So it can have a lot. This is an exclusive gate. This is actually what we call combinational logic. So right now this looks like it'd be a combination of ands and ors, right? But what we're going to do is we're going to come up here, and this is controlled by A, this is controlled by B, this is controlled by A, and this is controlled by B. So what I'm going to do is I'm going to do this. So right off the bat, if A is false and B is false, is this guy right here going to be true, output going to be true or false? So we'd be able to get through with this one. What's controlling this one? But we'd stop right there. We wouldn't get through this one, right? You understand? So right the way it is right now, it'd be false. So let's say I energize whatever's controlling A. So what would happen? This right here would open, right? And then this right here would close. So I'm energizing A, so the output would do what? Would go true. Okay. So let's say we come up here and we just energize B. So if I energize B, this output would go true, this output would go false. So I got a path through that here. So energize B, the output would go true. Okay. We know if I come up here and both of them are de-energized, we know the output is false. So let's press both of them. So I'm going to press both of them. Let me erase this first. So I press both of them. This will go true. This will go false. This will go true. So the output would do what? Would give us this. So what's this guy right here telling us? I missed one. So if I come over here and the output is false, what do I know about? Here's 0, 0, 0. What do I know about? Are they the same or are they the same? If I come up here and it has 0, 1, 1, 0. I'm going to put 1 out, 1, 0. But this circuit right here, we can literally tell if the inputs are the same or if the inputs are different. Well, I don't know how they're the same. I don't know how they're different. So if I come over here, this power here is true. I know they're different. Oh, I know they're so this is our comparison. These guys right here will always have 2 inputs, no more, no less. You see the way the symbol has changed. So here is a OR. So we're looking at this guy right here. This is an exclusive OR. This guy right here. Now, what this symbol, and people get confused, but what this symbol tells us what we get when the outputs are not the same. So, are not equal. So it's the opposite of the way the symbol goes. Sorry, that's the way it goes now. So this output, if I see this output is true, they're not the same. This output is false. So this output is false. Do they have the, yeah, they have this in the book here. So this is an exclusive NOR. In relays, in our PLC, we would wire it like this. I'm going to call this A, B, I'm going to call this A, B. So let's make these 2 like that. So right off the bat, I don't press either button. So A and B are both false. A and B are both false. So I will pass to the bottom one, right? So a 0, 0 would give me a what? Would give me a 1. I come over here and I press A. So if I press A, this contact right here would open. This contact right here would close. So I still don't have a path. You'll see that? So A, this would give us this right here. So the output would be a 0. Come down here. Erase this. And I press B. So if I press B, this contact will open. Oops, sorry. I forgot to erase this. This contact would open. This contact would close. So we don't have a path through here again. So that would be that guy right there. And then I'm going to come over here and I'm going to energize A and B. So A and B, this guy would open, this guy would open, this guy would close, this guy would close. Now we have a path through there. So this guy right here. So this guy right here says this is what we get when they're not equal. So if they're not equal, we get a low. If they are equal, we get a high. Or we get a true. And this is an exclusive NOR. So these are our comparators. So I get to compare how many things? 2 things. So an exclusive false when they're the same. An exclusive NOR, we get a true if they're the same. And then we're not going to deal with this is the IEC symbol. So these are ANSI symbols. What we use over here. This is what the PLC program is. So at the top that's an AND, then we have an OR. Then we have a NAND, so notice on a low active output, this is a triangle. Now this is an OR. It's got the same symbol as the OR, but it's got the little low active symbol. This is an exclusive OR. This is an exclusive NOR. Here's the output, they're equal, the output is low, and this right here is a NOT. So in PLCs, if you program using a logic block diagram, then these are the symbols you'd have to learn. But the Boolean algebra would be the same. But over here we teach this guy right here. Unfortunately, even the textbook teaches this, but you have to understand this book was written around RS Logic 500, and we don't have this other programming language available. Originally, PLCs were where? They were in the United States. So we used American standards, right? American National Standard Institute. When the web was first introduced and they were sending text, guess what code they used? They used the American Standard Code for Information Interchange, ASCII. And so it's still part of Unicode. So even though we've gone to that Unicode now, ASCII is still the first 250, 127, 128 characters in Unicode. But once these PLCs started moving into the international community, then we're starting to use international standards instead of just strictly American standards, right? Understand? So this book teaches this. This is what we have to use if we actually program the PLC using function block diagram. I'll try to set up one of these RS Logic, these 2400s to try to do this. If not, we'll just have to play around with it if you take an advanced class. So we're not going to worry about, so this is what Nancy likes. Nancy likes the Karnoff mouse. So this is a 4 input, so you got 16 in your chart. If you went to one, if you added one more input, your chart would have to have 32. If you went to one more input, you'd have to have 64 blocks. So we're not going to teach reduction in here. Like I said, I don't like K-mouse or Karnoff mouse. Nancy loves these things. I like Boolean algebra because to me it's just easier because I'm a math person. So we're not going to create equations in this class, even though if you were a really good programmer, this would be beneficial because take a look at the circuit, you could set up an equation for that circuit, and if it were reduced, then you would actually reduce the size of your circuit, right? Does that make sense? So very, very powerful. Except here we don't teach design, and the book doesn't do a great job either. So that's it, guys. So y'all know the logic, right? I programmed all the logic. I didn't do the ands. I didn't do the. So let me bring it back up this, and let's go offline. So what can we do offline? We can program it, right? So PLC's offline, so I can come up here, and let's come up here, and we'll add 2 rungs. Oh, if you don't do both, if you know your program's got, if you know it's got 5 rungs, right? Not including, you can just highlight one, insert 1 rung, and then after that you can just keep clicking on it, automatically sticks them in there for you. And what we'll do is we're going to come down here and we'll start off with this. And I'm going to put a down drop and pull this one in here and this one. So y'all understand down drops now. Are you okay on that, right? Oh, these are different than what they look like in motor controls. Motor controls are all even. But Allen Bradley, and it's even that way on RS Logic 5000. Via Portal, you actually do a down drop and you put everything you want to in there, and then you put an up, and it fits. So you don't put the up until you get everything in there. So down here, I'm going to do the same thing. I'm going to drag a normally open. So notice it turns green any place that you can insert it, right? And then we'll put a coil. And then down here, we'll come down here. let's do the down drop first. Okay. So we can do it that way. So if you know you're going to do one, and now it's a little easier because I don't have to drag, I can, so are there anything so far that you don't understand? So how many outputs do I have left? I think I'm dealing with output 4. So we got just enough. No, I don't. So the last one we have is 5, right? So we're okay. So I've only got one more output to work with. So let's, since we're not turning, since we can see it happen and we're not turning on lights, so let's use one of our B3s. So I'm going to call this A. What time is it? Okay, we're okay. I'm going to call this B. I'm going to call this A. Call it B. So y'all see what's so nice about symbols. So once I assign an address to a symbol, then I don't have to worry about the addresses anymore. I just type in the symbol name. And we'll call this A, B. So how many times can we use that? We can use them a lot of times, even though we're only being controlled by one switch or one output. A, B, and then we'll call this A, and we'll call this B. And then I'll come up here, what I'm going to do is, I'm going to come up here and delete output 0. So I'm going to delete our hand. So how do we delete? We just highlight it and hit the delete key on our keyboard. So now I've got, let's see, so I'm using 1, 2, 3, 4. I'm not using 0, right? So here I'll use the output 0. Oh no, I think, dang it. Oh, output 0. So I'm going to use output 0. Of course, it's going to get the same name. Average output 0/0. Oh, let me do that. Over here we'll use output : 0/5. So if you don't assign it a symbol, if you accidentally clip away from it, then you can right click on it and go to what? Edit symbol. Okay. And now we can give it a symbol. Now this is our exclusive. Okay. Check it for errors. It's good. Download it. You can actually hear it switch, by the way. Okay, so let's go down to the bottom. So this should be an exclusive OR, which means if the outputs are the same, it's going to be false, right? So here they're the same. Here they're the same, it's false. And here they're different. Down here on the exclusive NOR, it starts off true, right? Here they're different. Here they're different. Here they're the same. So your exclusive OR and your exclusive NOR will tell you right off the bat if the two inputs are different or the two inputs are the same. The exclusive OR, the output of the logic goes false if they're the same. An exclusive NOR, the output goes to a 1 if they're the same. And that's what gets people confused. So that's all. This is not actually a logic function. This is what we call combinational logic. Because it serves, and we can only, so how many inputs can I have on an OR? How many of these can I have on an OR? How many can I have? 2 or more. Great, that's the exact right answer. 2 or more. Gotta have at least two to get an OR, right? How many can I have on an AND? 2 or more. How many can I have on exclusive ORs and exclusive NORs? 2. No more, no less. And all we're looking is we're comparing 2 control devices to see if they're the same or see if they're different. And depending on what you want right here, what we're controlling over here, the lower or whether you want to use it. So if I want it to turn, all of them, then I'll use the water, I'll use the oil. If I want it to turn on if it's the same, I'll use the oil. And that's it for logic. And this has been around for years, just wiring contacts in series. So we've been doing logic long before we had logic gates, long before we had microprocessors that do logic. So that's one of the things we can do with this. Well, right now we're going to do logic. We're going to do logic with contacts. But later on, when we get into more advanced programming, let me go offline. And I'm going to start moving across my instruction palette. And we've got it right there, logical instructions. Can y'all see them? It's real little. We can do NORs, we can do ANDs, we can do ORs, we can do exclusive ORs, we can do NOTs, and we can cleave. Now what we'd do if we needed an AND, we'd take an AND and feed it into a NOT, right? Does that make sense? So, but these work on 16-bit numbers instead of contacts. So later on, we'll figure out what, not in this class. Like I said, how far are we going to go in this class? To timers and counters, right? We'll talk a little bit about this register, or not register. Your book calls these registers, by the way, which is totally wrong. These are called data files. So you won't find it, and you won't find the term register in the Allen Bradley manual. Usually a register is inside the microprocessor. These are not inside the microprocessor. Anybody had anything to do that? But the guy in the book calls these registers. These are not registers. These are data files. So on test, that's what I'm going to put. Since the book calls them registers, I'll put it in parentheses, but out beside them I'll put data files. So we can't access the registers inside our processor. These are data files. And so right now we know about inputs, we know about outputs. We don't know about status. We'll look at that. B3s, we know a little bit about that. We know we can use those for internal coil. We don't know how to use timers, but we know what timers do, right? You understand? It's going to delay something, and then counters. You know what counters do. We can have up counters, we can have down counters. MicroLogic 500 does not support up down counters. So that's our logic. Everybody okay? So now we can do what in our over here on our website? So we can go to this. We can come under here under course content. We can go to the chapter on what? Digital logic gates. And now we can do what? We can do the topical.